Hello and welcome to this video for CE 108. So in this video we are going to see how to use the method of section to find the internal loads, the internal moments, the internal shear in members that are subjected both to concentrated load and distributed load. So let's consider the example of a beam. The beam has a size 3L. And so the beam goes from x equals 0 to x equals 3L. At x equals 0, it is attached to a fixed support. And then at x equals L, there is a concentrated force with a magnitude F that is applied. And from x equal to L to x equals 3L, you have a distributed force that is applied with a magnitude W naught, which is equal to 2F over L. Remember that a distributed force is a force that is applied not at a point but over a distance, and in this case the unit of such a distributed load is in Newton per meter. It's a force per unit of length. So in this case it's in Newton per meter. That's why it's equal to F divided by L, a force divided by a length. So I'm gonna call this point A, this point B, C, D, etc. And so in this case, the goal is to find the internal loads, the internal shear, and the internal moment as a function of x, for x between 0 to 3L. So we want to find the load, the shear, and the moment for x going from 0 to 3L, which means that in this case, we don't want necessarily the internal load at a specific position, but we want to know the internal load everywhere throughout the beam, which means that we will need to consider different cases for different position x, and it also means that the answer might depend on x. It might be a function of x. So to solve this problem, we are going to apply the 5 steps that we have seen in the previous videos, the 5 first steps that should always be followed in a mechanics of material problem. So in this case, step 1, drawing the free body diagram. So we just did that. We have the free body diagram with the system, that is to say the beam, and the external forces, which is the concentrated force at F at x equal L, and the distributed load between 2L and 3L. Step 2, identify the unknowns. In this case, we have one reaction, which is the fixed support at x equals 0 at the point A. So fixed support means free unknown. In this case, we can define the unknown the way we want, going up, down, etc. It doesn't matter. But we can still use our intuition to define how we think the unknown should be defined. In which direction do we think the unknown are acting? So in this case, since you have the concentrated force F and the distributed load that are pointing downward, it is very likely that the support is going to apply a force that is going to oppose this motion. So it's going to be a force that is going upward. So I can draw it going upward directly, so that at the end I will find that this unknown force is going to be positive because I drew it with the right direction. Then, so you also have a horizontal force. This one is going to be 0 anyway, so it doesn't matter if I draw it going towards the right or towards the left. And then we have the moment, the unknown moment that is going to be applied by the fixed support. In this case, both the force F and the distributed load are going to create a clockwise moment about the point A. So in this case, the support is likely to oppose this clockwise motion by applying an anti-clockwise reaction moment. So in this case, I'm going to draw it in an anti-clockwise fashion so that at the end I will find a positive value for MA. If I draw those unknown forces and moments with another direction, that doesn't matter, but I will still just get a minus sign at the end after I apply the condition of equilibrium. Okay, so that was step 2. So now step 3, we are moving to the equation of equilibrium. So now what we are going to do is to project all of those forces and say that the sum of the projection of the force that are applied to the body should be 0. The projection along x should be 0, projection along y should be 0, and the projection along the projection of the moment about a given point should also be 0. So let's start with first the horizontal axis. So we are going to say that the sum of the projection of all the forces along the x-axis is going to be equal to 0. In this case, the only force along the x-axis that we have is NA. So NA is pointing towards the left, so it has a negative projection along the x-axis. And so in this case, it's the only one, so the sum is equal to 0, which means that in this case, NA is equal to 0. Second case, now we are going to say that the sum of the vertical forces, the sum of the projection of the forces along the y-axis, where I'm going to define y as going upward like this, the sum of all the forces, the sum of all the projection of the forces along the y-axis is equal to 0. So I'm going to take all the forces, project them on the y-axis, and say that the sum is equal to 0. So in this case, we have VA. VA is going upward. It's already in the direction of y. Its projection is plus VA since it's going in the same direction as y. The force F at x equal L is going downward, so it has a negative projection. So its projection is minus F. And then we have the distributed load. So here, when we write the condition of equilibrium, we need to calculate what is the resultant force associated to this distributed load. So in this case, it's it's a constant distributed load. So if I want to know its resultant force, I just need to calculate the area of the load diagram. In this case, the load diagram is a rectangle. So the resultant force is going to be the length, the product of the length over which the load is applied times the magnitude of the load. So in this case, the resultant force associated to distributed load is going to be equal to first the magnitude of the load, which is 2F divided by L, times the distance over which it is applied. In this case, it's applied over a distance L. So in that case, it means that the resultant force is 2F. The magnitude of the resultant force is 2F. And the force, we also need to specify at which point it is applied. In this case, it's always applied at the centroid of the load diagram. In this case, the load diagram is a rectangle, so the centroid is in the middle, which means that the force is going to be applied at 5L over 2, in between 2L and 3L. Okay, so now that we have this force, we need to project it along the y-axis to write the condition of equilibrium. So this force is going downward, so its projection will be negative. The magnitude of the force is 2F. And so the sum of those forces is equal to 0. So this allows us to find the value of the unknown VA, the resultant, the unknown force applied by the support. And in this case, we find that VA is equal to 3F. In this case, we find that VA is indeed positive. It means that indeed we drew VA with the right direction. We drew VA upward, and at the end we find that VA is positive. It means that indeed our intuition was right. So next, we are going to calculate the value of MA by saying that the sum of the moment is equal to 0. Here we need to choose about which point we are going to calculate the moment. So in this case, it's convenient to choose the point A to calculate all the moment about A, because you have several forces that have their line of action going through the point A, and that means that those forces are going to disappear, since a force for which the line of action is going through a given point does not create any moment about this point. So in this case, VA and NA will not create any moment about the point A, because their line of action is going through A. Okay, so let's see what we have. So in this case, the first moment that we have is the moment applied by the support. So we have MA. In this case, when we project the moment, we need to use the right-hand rule to find if the projection of those moments is positive or negative. So MA is anti-clockwise. It means it has a positive projection, so its projection is plus MA. Then we have the moment created by the force F at x equal L. So in this case, this force is going to create a clockwise moment, that is to say, a moment with a negative projection about the point A. So its projection is going to be negative, and the moment is going to be equal to the magnitude of the force times the arm of the force. In this case, the arm of the force is L. That's the distance between the line of action of the force F to the point A. So that's the moment created by the force F. Next, we need the moment created by the distributed load between 2L and 3L. So for this, we are going to calculate the moment created by its resultant force. So that's also going to be a negative moment, since it's creating a clockwise moment about the point A. And to get the moment, again, we need the magnitude of the force, which is 2F, times the arm of the force. So the arm of the force is the distance between the point A and the line of action of this resultant force, which in this case is 5L over 2. That is the arm of the force. And so the sum of all of those projections is equal to 0. This allows us to find the value of MA. And in this case, we find that MA is equal to 6F times L. We can quickly check the units, that indeed a moment is a quantity in Newton times meter, which indeed is equal to something that has the unit of Newton times a length that has the unit of meters. So the units match. So now that we have solved the value of the unknown NA, VA, and MA, now we know all the external forces that are applied to the member, and now we can use the method of section to find the internal loads that are applied that are experienced within this member. So next, we need to apply the method of section to find at each position X what is the value of the internal load, internal shear, internal moment. And for this, one of the first important steps is to figure out how many cases do I need to consider here. So in this case, we cannot directly pick any X between 0 and 3L and directly calculate the internal force, because when you use the method of section, you will cut the beam into two parts at a given X and then isolate either the left or the right. And here the problem is that depending on the position X that you choose, if you isolate, for example, the right part, the forces that are applied on the right will depend on the position X that you choose to cut the beam. For example, if you decide to cut the beam somewhere between 0 and L, and let's say you isolate only the left part of the beam, then in that case, the external force F will not be applied to the left part of the beam. But now, if you decide to cut the beam somewhere between L and 2L, now the force F, the concentrated force F, will now be applied on the left part of the beam. So now the forces that are applied on the left part of the beam are not going to be the same. And same thing, if you decide to cut the beam somewhere between 2L and 3L, now the forces that will be applied on the left part of the beam will be both the concentrated force F, and you will also have a fraction of the distributed load that will also be applied on the left part of the beam. So here we need to consider three cases. We need to consider what happens between 0 and L, what happens between L and 2L, and we also need to consider what happens between 2L and 3L. Those are the three cases that matters. Those are the three cases for which, after you cut the beam, you will have different cases regarding which forces are going to be applied either to the left or to the right part of the beam. one thing to one thing to note is that we don't need to worry about this position 5L over 2. So here, if you cut either slightly before or slightly after 3L over 2, that makes no difference, because the force that is applied at 5L over 2 is a fictitious resultant force. It's the resultant force of the distributed load. So that makes no difference whether you cut the beam before or after this position 5L over 2, because this force is not real. The force at 5L over 2 is not a real concentrated force. It's just a resultant force, the resultant of the distributed load. So remember that when you apply the method of section, you always need to go back to the initial distributed load. You cannot consider the resultant force anymore. So when we will apply the method of section to this domain between 2L and 3L, we will need to reconsider the initial distributed load and figure out what is the portion of this distributed load that is applied to the left part of the beam and what is the portion that is applied on the right part of the beam. But at this point, we cannot consider the resultant force 2F because this is not a real force. So there is going to be nothing special depending on whether you cut before or after 5L over 2. So in general, when you want to figure out what are the different cases that you need to consider when applying the method of section, you need to keep in mind that every time you have a concentrated force or a concentrated moment, like for example at x equal L, here we have a concentrated force, then you will need to consider to look at the method of section before and after this concentrated force. Concentrated forces and concentrated moments, they create some discontinuities in the distributed loads, so necessarily you need to do the method of section both before and after those those concentrated loads and concentrated moments. The second thing that matters is every time you have a distributed load that suddenly starts at a given point or suddenly stops at a given point, then again you will need to consider different cases depending on whether you cut before or after the distributed load starts, because in this case that will dictate whether a portion of this distributed load is applied or not to the section that you are isolating. So in general, you will need to apply the method of section everywhere in between the concentrated loads and concentrated moment, and in between the points at which you have a change in the distributed load. So every time you see some concentrated moments, concentrated loads, and every time you see some sudden change in the distributed load, then you will need to consider this as boundaries for the different cases. You will need to consider different cases in between all of those events. So in this case, we have two of those events, one concentrated load and one change in the distributed load. So that gives us 3 domains in between those two concentrated load or a change in distributed load. Okay, so now that we are going to do that, so we're going to consider those 3 cases, so case 1, case 2, and case 3, and apply the method of section for each of those 3 cases. So let's start with the first case, which is going to be x going from 0 to L. So it means that we are going to cut this beam somewhere at an arbitrary x position that can be anywhere between 0 and L. And so next, once we have figured out the first domain that we are going to consider, we need to decide, do we prefer to isolate the left part of the beam before this position x or the right part of the beam after this position x? So in this case, the answer that we get will not matter, will not depend on that. We can either isolate the left or the right, and we will get the same answer at the end. But we can still pick one or the other, depending on how we think it's going to simplify the calculation. So in this case, if we look at the right part of the beam, there is a lot of forces, a lot of distributed loads. So in this case, it's probably going to be easier to consider the left part of the beam. So we're going to consider this left part of the beam and isolate it. So in this case, we are at step 4, method of section. So in this case, it's useful to redraw the left part of the beam here that we are isolating to make sure we are not forgetting any force that is applied to this portion of the beam. So let's redraw our new system, the new fraction of the beam that we are isolating. So in this case, we are going to consider now the beam that goes from x equals 0, so that's the beginning of the beam, up to the specific x here. This is the x at which I'm cutting. So now the position x at which I'm cutting the beam, this is where this system is going to end. And now let's see all the forces that are applied to this portion of the beam. So what do I have? First, I still have the reaction of the support at x equals 0. So there is still VA, which is equal to 3F. So this one I already found its value, so I can just replace VA by 3F. NA, we know it's equal to 0, so I'm not going to write it again. And then we have the moment MA, which we found previously to be equal to 6FL. So those are the forces and moments on the left. And then on the right, now we are going to have the forces that are applied by the right part of the beam to the left part of the beam. So we are cutting the beam at x at a given position x. So now the right part of the beam is acting as a fixed support, just like a fixed support to the left part of the beam. The right part of the beam is going to prevent the left part of the beam from going up and down, from going left and right, and from rotating, because the left part has to be attached to the right part of the beam. So it means that now we have 3 unknowns, which are the normal force applied by the right to the left, the vertical force applied by the right to the left, and the moment applied by the right to the left. So we have those 3 unknown forces, just like what we would have for a fixed support. And those 3 unknown forces are going to be the internal load, internal shear, and internal moment that we are looking for. Okay, so let's define those forces, and for this we are going to use the sign convention that we use in this class, which is that if you isolate the left part of the beam, then we always define the normal load as pointing towards the outside. We define the internal shear as going down, and we define the moment as being anti-clockwise. On the other hand, if we isolate the right part of the beam, then again we define the internal load, this time going towards the left, so that it's still pointing towards the outside. We define the internal shear as going up this time, and we define the internal moment as being this time clockwise. The reason we have this sign convention is to ensure that we always find the same value for the internal load, internal shear, internal moment, irrespectively of whether we isolate the left or the right, since we know that due to the principle of action-reaction, the force applied by the left will be equal to the force applied by the right, but with an opposite sign. We need to define those forces with an opposite direction. The force applied by the right to the left has to be going to the opposite direction as opposed to the force applied by the left to the right. Okay, so let's define those internal loads in this case. So we have the internal load here at the point x. I'm going to write this n of x. That's a force that can potentially depend on x, so I'm going to write it as a function of x. I'm going to use the positive sign convention, so it's pointing towards the outside. Then we have the internal shear, V of x, pointing downwards according to the sign convention, since I'm isolating the left part of the beam, and the internal moment that I'm going to write in an anti-clockwise way according to the sign convention. And now that we have this, we just need to go to step 5 and apply the condition of equilibrium to this subsection of the beam to find the value of those internal shear, internal load, and internal moment. So let's start by the fact that the sum of the forces, the sum of the projection of the forces along the x-axis is equal to 0. In this case, the only horizontal force is n of x. It has a positive projection, so it's equal to 0. So in this case, it means that the internal load n of x is equal to 0. So let's move now to the sum of the projection of the forces along the y-axis is equal to 0. What do we have? So y is going upward, so we have the force 3F that has a positive projection. We have the internal moment V, the internal shear V of x. It's going downward, so it has a negative projection. So here one thing to remember is that we use the sign convention to decide whether we want to draw the internal load or the internal shear or the internal moment. We use the sign convention to decide how we want to draw it. For example, in this case, we use the sign convention to figure out that we need to draw the internal shear as going downward. This is because we have isolated the left part of the beam. If we had isolated the right part of the beam, then we would have drawn the internal shear as going upward. But now that we have used the sign convention to decide how to draw this internal shear, now we still need to project it along the y-axis. And in this case, the sign of the projection does not depend on the sign convention. Now we need to project this force. This force V of x is going downward, so it has a negative projection along the y-axis. The y-axis is going upward, but the internal shear is going downward, so it has a negative projection. So when I write the condition of equilibrium, here you have a minus sign. If I was isolating the right part of the beam, then this internal shear would be going upward, and in that case it would have a positive projection. So I would write plus V of x. This projection would be positive. But in this case it's going down, so its projection is negative. Again, you will find the same answer at the end depending on whether you are isolating the left or the right. Okay, so in this case, those are the only forces that we have along the y-axis. So the sum of those projections is equal to 0. And so in this case, we find that the internal shear is equal to 3F. So we have found the value of the internal load. We have found the value of the internal shear. This is, those forces are constant for x going from 0 to L. So now to find the value of the internal moment, we are going to write that the sum of the projection of the moment is equal to 0. So every time you write the sum of the moment, remember that you need to specify about which point you are defining those moments. So in this case, whenever you use the method of section, it is always convenient to calculate the moment about the point x at which you are defining your section. That way, both the internal shear and the internal load will have their line of action going through their point x, so they won't appear in this equation. Okay, so now let's write that the sum of those moments is equal to 0. So what do we have? First, we have the internal moment at x. So this one will contribute to this beam. In this case, again, we decided to draw this moment m of x as being anti-clockwise due to the positive sign convention. This is because we have isolated the left part. If we had isolated the right part, we would have drawn this internal moment as being clockwise. This has nothing to do with the sign of its projection. Now, when we project the moment, we just need to look, is it clockwise or is it anti-clockwise, just like any projection. So now we look at this moment m of x. It is anti-clockwise, so it has a positive projection. So I'm gonna just write it with a plus because it has a positive projection. So v of x and n of x do not create any moment about the point x, since their line of action is going through this point. Now what do we have? We have the other moment at x equals 0. It's also a moment with a positive projection, so I'm going to write this moment with a positive sign. And finally, we have the moment created by the force 3F at x equals 0. This one is creating a negative moment about x. So it's going to have a negative sign. Its projection is going to be negative. And its the moment is going to be equal to the magnitude of the force, which is 3F, times the line of action of the force. In this case, the line of action is this distance here. This is the line of action. This is the distance between the arm of the force to the point x. And in this case, this distance is equal to x. So this is not a general case. This is only what you find in this case. The distance between the arm of the force and the point about which you are calculating the moment happens to be equal to x. So the sum of all of those projections is equal to 0. So that gives you the value of the internal moment, which in this case is equal to 3F times x minus 2L. Okay, and in this case, we find that this internal moment depends explicitly on x. It means that as you go from different position from x equals 0 to x equal to L, the internal moment is gradually changing. It's increasing. As you increase x, the internal moment is increasing. So in this case, the internal moment explicitly depends on x. It's a function of x. Okay, so we have solved the first part of the problem. We have found the value of the internal load, the internal shear, and the internal moment as a function of x everywhere for x between 0 to L. So now we need to consider the second cases, which is when x is going somewhere between L to 2L. Okay, so let's do this. So now we consider the case where x is somewhere between L and 2L. So we are in between the concentrated force and the distributed load on the right. Okay, so in this case now, it means that we are cutting the beam at an arbitrary position x, somewhere between L and 2L. Okay, so now we need to decide again how we are going to isolate the left or the right. So here you are pretty much in between the beam, so you can you have pretty much the same level of difficulty depending on whether you isolate the left part of the beam or the right part of the beam. So to make it consistent with the previous case, I'm going to isolate the left again, but you could have isolated the right part here. So now it means that I'm isolating the left. Remember that when you isolate the left, you need to isolate everything, the entire part of the beam that is on the left of this x, which means that you need to isolate this part here, but you also need to isolate everything in between, like up to the very left of the beam. So here we need to isolate the beam everywhere between x equals 0 to the specific x at which you are cutting the beam. So not just simply from L to x, we need to isolate the entire part of the beam that came before x. So everywhere in between x equals 0 to the x at which we are cutting the beam. To make sure we are on the same page, let's redraw the part of the beam that we are isolating. So in this case now, the new system that we are considering is the part of the beam that goes between x equals 0 to x equal x, the x at which we are cutting the beam. So it means that now, since we are isolating the left, the forces that will be applied on this beam will be the forces due to the fixed support at x equals 0. But now, since we are cutting somewhere between L and 2L, we will also have the concentrated force F at x equal L, which is also going to now apply to the left part of the beam. So this is why we needed to make two distinct cases depending on x is between 0 and L and 2L, because depending on whether we consider those cases, the concentrated force F will either be there or not. So we need to consider those two cases. The forces that we have at x equals 0 are still the same. We have the vertical force 3F, and we have the moment equal to 6FL. Okay, so that was the method of section. So now we are going to apply the condition of equilibrium on this part of the beam that we have isolated. So let's do that. So again, sum of the projection of the force along the x-axis is equal to 0. So in this case, we just need to not forget the forces that we are actually looking for, which are first the internal load. Again, we define it as pointing towards the outside. We are isolating the left part of the beam, so it's pointing towards the right, pointing towards the outside. Now we also have the internal shear, which again is pointing downward since we are isolating the left part of the beam. And we have the internal moment, which is still anti-clockwise since we are isolating the left part of the beam. Sum of the forces along x equals 0. Here in this case, there is only n of x, which has a positive projection, so it's pointing towards the positive x. So in this case, this force n of x is equal to 0. Second, sum of the projection of the forces along the y-axis. So what do we have in this case? We have the force 3F pointing towards the positive y, so it has a positive projection. Next, now we have the force F, concentrated force F at x equal L. It's pointing downward, it has a negative projection, so it comes with a minus sign. And we have the internal shear at x, at the position x at which we are cutting the beam, is pointing downward, so it comes with a negative sign, it has a negative projection. Sum of those forces is equal to 0. This allows us to find the value of the internal shear, which in this case is equal to 2F minus F, so it's equal to 3F minus F, so it's equal to 2F. So one thing to note here is that when we looked at this internal shear between 0 and L, we found 3F. Now that we look at the internal shear between L and 2L, now we find 2F. It means that the internal shear has suddenly changed before and after x equal L. This is because you have a concentrated force at F equal L, and as we mentioned previously, concentrated force will induce some discontinuities in the internal loads, which means that because you have this concentrated force at x equal L, you have a sudden discontinuity. The internal shear is suddenly changing as you go from slightly before x equal L to slightly after x equal L. So just like in mathematics, here you have a discontinuity where the value of the function v of x is suddenly jumping at the point x equal L. This is why the internal shear, internal load, internal moment are not defined at the point where concentrated loads are applied or concentrated moments are applied. This is because concentrated forces and concentrated moment are inducing some discontinuities in the internal loads at those points. So the internal loads are not defined at the points where you have concentrated loads and concentrated moments. So we can only calculate the internal shear in between 0 and L, and then in between L and 2L, but we cannot calculate the internal shear exactly at x equal L, because this is a point where you have a discontinuity. Okay, so finally now if we want the internal moment, we need to consider the sum of the projection of the moment. Again, we are going to consider the sum of the projection of the moment about the point x. So what do we have? First, we have the moment at the point A. It is still a moment with a positive projection, so it's plus 6FL. Now we have the moment created by the force F. The force F is creating a positive moment about the point X. It has a positive projection. The force F is going to make the beam rotate in an anti-clockwise way about the point X, so it's a positive projection. The value of this moment is going to be equal to the intensity of the force, which is F, times the arm of the force. In this case, now the arm of the force is the distance between the line of action of the force to the point X. So in this case, this arm of the force is the distance. It's X minus L. That's the distance between the arm of the force and the point about which you are calculating the moment. So now we also have the moment created by the force free F at x equals 0. This time this force is going to create a negative moment about x. It's going to make the beam rotate clockwise about F. So according to the right-hand rule, this is going to create a negative moment, a moment with a negative projection about the point X. So its projection is negative. The moment is equal to the intensity of the force, which is free F, times the arm of the force. Now the arm of the force is the distance between the line of action of this force free F to the point X. This is, in this case, X. This is the arm of the force. Okay, so we have this moment. The last moment that we need is the internal moment at X, the point at which you are cutting the beam. This one is a moment with a positive projection because it's anti-clockwise, so its projection is positive. And the sum of all of those moments is equal to 0. So now we have everything we need to calculate the value of the internal moment. And so in this case, the internal moment is equal to F times 2x minus 5L. So in this case, the internal moment also depends on x. It explicitly depends on x. So now finally, the last case we need to consider is the case where x is somewhere in between 2L and 3L, which means that now we are considering a given x that is somewhere here between 2L and 3L. Remember that in this case, it doesn't matter whether x is larger or lower than 5L over 2, because this force that is at 5L over 2 is not a real force, it's a resultant force. So there is going to be no discontinuity in this case in the internal shear. This is not a real force. We will need to go back to the distributed load when we apply the method of section. Okay, so in this case, again, we need to decide whether we isolate the left or the right. In this case, it's going to be easier to isolate the right part of the beam because there is a lower number of forces that are applied on the right than on the left. So we are going to now isolate this time the right. Okay, so let's redraw the part of the beam that we are isolating. So now it means that we are isolating the right. So we're going to isolate the entirety of the beam that is on the right of the point X at which we are cutting the beam. So let's redraw this part of the beam. So now it means that the part of the beam that we will be isolating goes from the point X at which we are cutting the beam up to 3L, which is the right extremity of the beam. So what are the forces that are applied on this portion of the beam? So now to get the forces, we need to consider what is the fraction here of the distributed load that is applied on the right part of the beam. So we know that this distributed load is still having the same intensity. The intensity is constant. its intensity is still 2F divided by L. But now we need to recalculate what is the new resultant associated to this portion of the distributed load. So we will get now a new resultant force. This resultant force is going to be applied in the middle. So it's going to be applied in the middle between x and free L. So the position at which we will get this resultant force is free L plus x divided by 2, the middle in between x and free L. And now we need to get the intensity of the force. The density of the force is still equal to the value of the distributed load. So it's equal to 2F over L, that's the distributed load, times the distance over which it is applied. The force is equal to the area of the load diagram. So the load diagram, the area of this load diagram is equal to the intensity of the distributed load, 2F divided by L, times the distance over which it is applied. And in this case, the distance over which it is applied is the distance from x to free L. So the distance is free L minus x. Okay, so we have the new resultant force associated to the portion of the distributed load that is applied on the right of the point x at which we are cutting the beam. And now we need to add the force that we are looking to find, which is the internal load. So now remember that now we are isolating the right part of the beam, so we need to use the other sign convention as compared to the one we previously used. The internal load is always pointing towards the outside, so now we're going to make it point towards the left. This time the internal shear will be pointing up according to this sign convention. It's pointing up, and we are going to this time draw the internal moment at x equal at x as being clockwise. This is according to the sign convention that we are using when we are isolating the right part of the beam. So that was step 4. Now let's move to step 5, the condition of equilibrium. Sum of the forces along the x-axis is equal to 0. As usual, we only have the n of x. In this case, n now has a negative projection along the x-axis, so its projection is negative. The sum of the forces is equal to 0, which means that n of x is equal to 0. There is no horizontal force in this problem. Let's consider what's happening along the y-axis. So what do we have? We have V of x, the internal shear. Now the internal shear is pointing up. So the internal shear now has a positive projection. Again, the sign convention that we use for the internal shear tells us, depending on whether we isolate the left or the right, it's telling us whether we need to draw it pointing downward or upward. But now when you write the condition of equilibrium, you need to project those forces. So here it's pointing up, so it has a positive projection. Before it was pointing down, so before it had a negative projection, but now it's pointing up, so it has a positive projection. So we always draw the internal shear, internal load, internal moment with the positive sign convention, but then its projection can either be negative or positive depending on whether it's pointing up or pointing down. Next, the only vertical force that we have besides V is the resultant force associated to the distributed load. It's pointing downwards, so it has a negative projection, and in this case the intensity of this force is 2F divided by L times 3L minus x. That's the resultant force that we calculated. The sum of those forces is equal to 0. So this allows us to calculate the value of the internal shear. So the internal shear is just equal to 2F divided by L times 3L minus X. Another way to write this is that the internal shear is equal to 2F times 3 minus X over L. And we can check that indeed the unit of the internal shear is a force, so its unit should be in Newton, and this thing is equal to some newtons, and this thing is meter times meter, so it's dimensionless, so we have some newtons equal to some newtons. Now the last thing we need is to find the value of the internal moment. For this we are going to write that the sum of the production of the moment about the point X is equal to 0. So let's do that. Sum of the moment about the point X is equal to 0. So what do we have? We have the moment at X, so the internal moment m of X. This time the moment m of X, because we are now isolating the right, the moment m of X is defined as being clockwise, and because it's clockwise now it has a negative projection. So when I write the condition of equilibrium, I need to write its projection, which is now negative. So I have to write minus m of X. What else? So we have the moment created by the resultant force at the one that is applied at the middle of this portion of the beam. So this force is going to create a negative moment about the point X, so I'm going to add a minus sign to calculate this moment. So this moment is going to be equal to the magnitude of the force. The magnitude of the force is 2F divided by L times 3L minus X, and I need to multiply by the arm of the force. The arm of the force is here. It's the distance between the point X and the line of action of this force. So in this case, this distance here is equal to the distance going from X to the middle of this beam. So in this case, this distance is 3L minus X. This would be the entire length of the beam, and if I divide by 2, then I find the arm of the force. And so the sum of all of those moments is equal to 0. So now I have everything I need to calculate the value of the internal moment at X. So it is going to be equal to, so it's going to be negative. It's going to be equal to 2F divided by L times 3L minus X squared. And so here you have the factor 2 that disappears, so we can remove the factor 2 here. Okay, so that gives us the value, the result that we need. So that gives us the value of the internal moment as a function of X. So now we find that the moment here is having a parabolic relationship. It depends parabolically in terms of X. So now we have solved this problem. So we have found the value of the internal load, the value of the internal shear, the value of the internal moment, and we have found this for every X in between 0 to 3L. So we have considered those 3 cases, and in each of those 3 cases we have the expression of internal load, internal shear, internal moment, and those loads depend explicitly on X. So to provide the answer to this problem, we just need to write those relationship to provide the expression of how those 3 quantities, the internal load, internal moment, and internal shear, explicitly depend on X in each of those 3 domains.